This is Industry Spotlight. It is a series of webinars from a corporate liaison program of IEEE Santa Clara Valley section. Paolo, myself, and a few others are running this program. We are attempting to gather a corporate around this program, and this webinar is just one of the so-called products we have. Today, this is the 22nd installment of the webinar, and it's our great honor and pleasure to host Ian Foster. Ian Foster has a long bio. I'm not even attempting to read it. I've known him since the grid days and even before. He is well known for Globus. He is one of the developers of Globus. Most recently, he is most well known for FunkX, that I have deep technical interest in. And he has been also awarded ACM IEEE Ken Kennedy Award most recently. If I have missed anything important, Ian, please add. Ian will be talking about federated function as a service for flexible scientific computing. Ian.
Okay, thank you very much, Dejan, and thank you everyone for joining this evening. So right, I'm Ian Foster. I'm both at the University of Chicago and Argonne National Lab, which is two wonderful institutions. And I'm going to talk today about federated function as a service as a concept and how we've realized it in this FunkX system, and then how we're applying it in the context of scientific computing. I think the concept and software is broadly applicable, but that's where we found our motivating applications and where we've been exploring its application. And I should mention, this is joint work with a wonderful team. Kyle Chard, in particular, sort of leads the FunkX project on a day-to-day basis. Dan Katz is very involved, and a number of other wonderful developers and scientists, mostly at the University of Illinois and at the National Center for Supercomputing Applications, but we also have contributors from elsewhere. So let's make sure I can make this work. Okay, so a motivation, from a scientific perspective, is integrate. We're very interested in ways we can integrate computation into a wide variety of scientific workflows and applications. We're living in a world in which hardware, of course, is becoming increasingly specialized. We have access to immensely powerful supercomputers, specialized accelerators, often deployed near scientific instruments, various specialized machine learning hardware in our labs. And then we want to run these interesting workflows in these heterogeneous environments, real-time interactive workloads, for example, for steering of scientific experiments, various machine learning training and inference workflows, and then high throughput computations where we just want to run hundreds of thousands of tasks. And each of these may be better placed in a different environment. And then finally, we're working, we want to make this computation accessible to people from many different backgrounds, many of which want to integrate these tools directly into their applications, but others want to use things like Jupyter notebooks and other similar things. So as a bit more context, Dejan mentioned Globus, so I'll just say a couple of words about that. We've been working for the last 10 years or more now, building sort of software as a service capabilities for large-scale data management, using what's sometimes called hybrid software as a service. The Globus software runs on the Amazon cloud, but it supports the access to and movement of data, management of data on tens of thousands of scientific lab computers of different sorts, from supercomputers down to individual laptops, providing, we would say, the reliability and manageability of SAS with the local access to storage systems that's required to manage scientific data, which inevitably is distributed. That some of it may be in the cloud, much maybe in scientific supercomputer centers, much more is in various research labs. So Globus, if you like, forms this universal authorization, authentication, and data fabric that spans most major research universities in the US and many other places else in other locations. Using this, as I mentioned, this hybrid SaaS model, which I think we were sort of pioneering and using in the scientific setting at least, but is now becoming fairly widely adopted. Fancy management sitting on the cloud, highly reliable, replicated, using innovative cloud services of various sorts from Amazon, which is the provider we've chosen, but then connecting these little Globus Connect agents that run on storage systems in many different places. And FunkX then in that context is basically trying to leverage those same ideas, but instead of accessing data anywhere, we have a Globus Connect agent deployed. We want to be able to run functions anywhere that FunkX is deployed. And let's say a few words about function as a service. So I'm sure we're all quite familiar with it, offered by cloud providers as a wonderfully lightweight and flexible way of accessing computation on a very much a pay-as-you-go model. Running on the Google Cloud, I will submit requests to run functions, and I can submit one function request or a million function requests, and the appropriate resources will be provisioned for me. Similarly on the Amazon Cloud and Microsoft Cloud and so on and so forth. And some of the nice features here are, simple, straightforward, single provider submission mechanism, homogeneous execution environment, this elastic scaling that I've mentioned already, and typically integration with the data management services provided by the cloud provider. So what we want to say is, well, could we basically provide the same interface, but the same simplicity of interface and auto scaling and so forth, but putting behind that interface not the resources of a cloud provider, but the resources that sit in our research labs. And why would we want to do that? Well, maybe it's because we're cheap and that's what we have free access to. But a bit more fundamentally, actually, it's because we want to be able to leverage the specialized resources that we have located within our labs, other people's labs, the national supercomputer centers, et cetera, each of which have unique capabilities. We also want to be able to send requests to cloud providers as well, but we also want to be able to perform this edge computing where the resources are available. And we still want the same capabilities as offered by centralized cloud in this federated cloud environment. So the result is this system we've been building for the last 2 or 3 years, FunkX. It's cloud managed, but federated function as a service, just like Globus is cloud managed, but federated data as a service. How does it work? Well, we have a cloud hosted service to which we send requests to perform computation and to which we register and share compute endpoints. We can register and share Python functions, and then we can request execution of those functions just with, as we would do with conventional function as a service, but with the functions being executed at these remote locations. The FunkX logic also managing the staging of function implementations to the places where computation needs to occur. And if you're want to try some things as we're talking, well, there's lots of information at funkx.org, and also a pointer to the Binder virtualization environment, so you can try running things without deploying things on your own computers. So this is the model. Let's now look at some of the ways in which people use it. I think most of this has been covered already, but I'll just point out a few more details. So an endpoint some of the concepts here, actually just two concepts really. The endpoint is a place where a FuncX agent is deployed. It could be and indeed it is, my laptop. That FuncX agent simply starts processes running on my laptop, or it could be a 100,000 core supercomputer, in which case, typically what will be happening is when I start running functions, I start dispatching function requests to that endpoint, there'll be some dynamic resource provisioning going on via interactions with the queuing system on that supercomputer. So there's a variety of different implementations, but they all support the same Python implementations. Then under the covers, well, we've got this FuncX service, which supports the single interface. We've talked about most of this. A key thing I won't say much about, but that is very important, is an OAuth-based security model, which supports, really importantly, the delegation mechanisms that we need if we're going to have a user ask FuncX to run programs on their behalf on a third-party computational system. Okay, let's move on. So what I'm going to do now is talk through some of the use cases we see people using this system for. Then I'll look about how we actually use it and give a few performance results. So one rather trivial but important use case is simply executing a large number of tasks. It could be, machine learning model inference tasks or a set of simulations on one or more remote computers. So this is the sort of thing that one might use a system like Condor for example. FuncX makes these things particularly simple. So I submit my 100,000 requests. FuncX caches the tasks until they can be executed, caches the results as they come in, and then I can connect later and retrieve the results. And under the covers, it will be scaling to provision results as needed. And I show a couple of examples underneath that people have used it for. Machine learning-based drug screening. I've got a machine learning model trained to see whether a particular small molecule will bind to a COVID protein, looking for anti-COVID therapeutics. And I want to be able to run millions of those functions on some large computing system. And then high energy physics does similar things for statistical inference, processing large numbers of potential models against their experimental data. Then this is actually the high energy physics example. They have a little web interface that allows people to say, here's some new data, run all available models on it. And the back end here is a parallel cluster at Chicago. The results, of course, are a major speed up thanks to the ability to use all processors. So you might say, and of course you'd be right, this is just trivial parallel processing in this case. And the nice thing is that this trivial parallel processing is very easy to perform. A slightly bigger example, one of our colleagues at the University of Chicago, Eric Jonas, is interested in models for inverse spectroscopy. So we have well-known methods for taking a molecule specification and predicting or computing, if you like, its spectra, as would be measured by spectroscopy. The inverse problem, giving a spectrum, working out what the molecule is more complicated, but he's developed powerful techniques for doing this, but they're computationally intensive. So he's typically running 100,000 tasks now, each maybe consuming tens of core hours. So this would take a long time on a workstation. He's able to do it in, he says a month. I guess that's still a long time, but for him, an interesting speed up using resources at the University of Texas. So that's one use case. Another for me, much more interesting use case is in the context of experimental data analysis, where we're collecting data from a scientific instrument. In our case, it could, of course, be other, you can certainly imagine other non-scientific applications. And the analysis pipelines, which we have got very good at automating, need to perform various forms of computation. And we want to be able to perform some of those next to the instrument because the data is large or the response time requirement is small. Others is small, and others we want to perform, perhaps we would prefer to perform remotely because the amount of data is perhaps smaller, but the amount of computation required is larger. And so we're using this for example, for various light source data analysis applications. And I'll show you a couple of examples. So these sort of show the pipelines that we're dealing with. I don't think I'll go into details given time availability, but just point out these pipelines include, steps involved of data collection, data movement, data reduction, structure refinement, in this case, which is dealing with COVID protein structure determination, and then later on tasks relating to, for example, data cataloging and data publication. So a mix of different task types. And the computational tasks we want to be able to flexibly direct to different computers, and we use FuncX for that purpose. I think I have here's another example that sort of shows in more detail the typical flow: authentication, data transfer, FuncX computation, human interaction to perhaps perform some review of results, then more computation to extract metadata, and then more transfer, then data publication. And these graphs show some examples of what the resulting pipelines look like in more detail, the orange being computation. And you'll see, of course, as you might expect, a wide variety of computational durations associated with these different light source data analysis pipelines. Most of them, ranging from a few seconds up to hundreds of seconds. So we're not looking at sub-millisecond round trip times here, but certainly reasonable size. But they work well with FuncX. So here at the bottom we show another pipeline, another representation of one of these pipelines, the high energy diffraction microscopy one, the first one in the picture. Again, you'll see a mix of transfer and mostly compute tasks and some data publication tasks. And each of these may end up being redirected to a different computer in our computing environment. In fact, they can be redirected to any computer that runs a FuncX agent. I'll skip over that. And then, the third use case that we see occurring, and this one increasingly often, is people building FuncX into more advanced, sophisticated applications. So basically, the FuncX API is serving as a platform for building applications that need to be computationally powered during their execution, if you like. So, for example, the Data and Learning Hub for Science, DL Hub, is a system for publishing machine learning models with a scientific focus, and then for potentially training those models, and then very much performing inference with these models. So DL Hub, cloud hosted, receives a constant stream of requests to train and run models, and it outsources the training and running tasks to available computers using the FuncX API. Here's another example of a platform. This one is from Argonne National Lab. The Machining and Manufacturing and Machine Learning platform is a system for running experiments relating to advanced manufacturing processes. Those experiments, for example, flame spray pyrolysis, one runs various gases through a chamber at high temperature. They combust in various ways, and one then analyzes the reaction products using spectroscopy, referring back to the earlier application. And one wants to be able to dynamically adjust the combustion conditions based on what has been learned from observing previous conditions. So it needs rapid computing on demand for that purpose. So they use function as a service, FuncX for that purpose. Okay, so where are we at this point? So we've been building FuncX for I guess 3 years now. We have support from the National Science Foundation to productize it. We have a growing number of people contributing, a growing number of people using it. The numbers here may either seem large if you're an academic working with a research product, or tiny if you're a Globus developer, which of course has billions of requests, or a commercial function as a service operator, which similarly have probably trillions of requests. But we certainly are learning a lot about how to operate the system, and I think are now getting to the point where we can scale it up yet further. So a few interesting things here. Large numbers of, or modest numbers of endpoints, 4,000 or so. Quite a few registered functions. People register new functions continuously, it seems. The average function runs for a couple of minutes, so that helps guide our optimization strategies. And the number of invocations is modest but growing. Okay, so that's sort of an overview. If anyone has any questions at this point, we could take them. Otherwise, I'm going to drill down on some of the details of how we implement the system and how you use it, and some things we've learned from implementing it so far.
You can either type in the chat or just ask, and after a few minutes, we'll let Ian continue. I sure have a bunch of questions, but I'll leave them for the end.
Okay, well, I'm happy to continue. So let's go. Remind us now. So we've got this, the function as a service. Typically, like we've explained the concepts. The nice. Why I think one reason why people like it is this ability, this very intuitive and lightweight interface to remote computing. I can define a function. We tend to use Python, but it doesn't have to be that. I can use some simple function calls to publish it, and then I can invoke it without concern for where it's going to run or what resources will be provisioned to run it. In the context of FuncX, how is that model implemented? Let me show a few pieces of code just to give you the idea. Well, first of all, of course, many people will be running FuncX on a existing computer that is FuncX enabled, but so they can skip this step. But if not, then installing and configuring and starting a endpoint is a matter of a few simple command line calls. I install the FuncX endpoint software. I configure an endpoint, what I'm calling here my EP, and then I start the endpoint. And at that point, or as part of that process, I obtain a UUID for the endpoint, and I can then dispatch function requests to it. There are variants of the endpoint that basically are designed to support a laptop, workstation, a multi-processor cluster, a cloud system, a supercomputer, basically with the details varying according to how they interface to whatever resource management system is available on those computers. But those details are mostly hidden from the end user. And we also, of course, when we dispatch a computation to run on a remote computer, if it's a pure Python library, it may be able to run without any special configuration, but we also want to be able to run other things, so we also support Docker, Singularity, and Shifter containers as well. So I might say a bit more about that later. Okay, so this is my optional endpoint configuration step for the agent. Assuming that we have some agents deployed and I have access to them, then I can go ahead and in my Python code create a func client, perhaps register a function that I want to run. This is the arguably simplest possible function that I could define. It simply returns a string, hello world. I'll print the UUID that identifies the new function that I've published. I then determine the UUID for my funcx endpoint, and then I run the function that I've just published on that endpoint, providing perhaps some arguments if such are required, and then I retrieve the results when I'm finished. So this looks a bit like a typical function as a service thing. It looks very similar, in fact. One interesting variant is that I can submit something and then later on retrieve the result, perhaps while disconnecting in the meantime. So the results are stored in the cloud, actually currently in the Amazon cloud, from which I can retrieve them. But the computation is occurring on my laptop or my exascale supercomputer, once we have one. Okay, so that's my funcx implementation slide, or how to use slide. Now let's look at some aspects of its implementation. So we're sort of interested in performance from a few different perspectives. One is how well it can scale the execution of a fixed number of concurrent functions. And we look at supercomputers because that's what we have access to, and there are users like Eric Jonas, as mentioned before, who care very much about the time required to run a large number of concurrent functions, but certainly not the only use case. And at present we find for running, in this case 100,000, we scale well up to about 2,000 containers, even with essentially empty no-op tasks. And that's what we're showing here on two different computers, Theta and Cori. Doesn't really matter. They're at Berkeley and Argonne. It doesn't really matter, I suppose. Running either tasks that perform a no-op, the solid lines, or that sleep for a second, or indeed another task that runs for a minute. And we look at the performance we get. And we see that after about 2,000 cores or processors, containers, I guess, we performance levels off. But a different measurement is to scale the number of tasks to be run with the number of containers or cores. And here we scale, see that this is the results on the right. And here we see we can scale up to 130,000 concurrent containers. I think that was the largest number we could run on the machines that we had access to. So I guess these results simply show that the implementation does sensible things. And I would point out that other function as a service systems don't scale in this way. So they haven't done such sensible things as we have done, perhaps because they're not targeting the high degrees of scalability. Here's sort of a summary slide on things we've learned from applying funcx to science use cases, and perhaps it's it might be worthy of some time discussing. So things we've found from studying, our initial set of 300 or so users, things that work. So we have been able to successfully abstract the complexity of using a wide variety of compute resources. Some of you may think that's a wonderful thing if you have experience trying to do that yourself. Others might think it's trivial and obvious if you've used primarily cloud systems, but certainly the fact that we can now write in a few lines of code this functions that will run on dozens of different computers is a tremendous simplification of where things used to be, and turns out to be surprisingly useful. I would say it is usable, but useful for a wide variety of scientific use cases. I think people have also found that this automatic scaling with a single interface is valuable. So behind the covers, of course, if I'm running on my laptop, I'm running one thing at a time, typically, in the order they come in. So that's not very complicated. I could configure my laptop to run more things at a time, and that will also work well. But on a supercomputer, I may configure it to be able to scale up to, say, 100 or 1,000 concurrent workers, as we call them, the things that sit on cores and run jobs. And that scaling will then occur automatically without any user intervention, and that is also appreciated. The authentication model is really pretty much invisible, but is really vital. So, recall what we're doing here is we have users submitting requests to this cloud-based service, asking them to run requests not on a cloud that is subject to management by a single central cloud provider, but perhaps on dozens of different computers, each managed by different resource providers, so that security requirements can be quite complex. And using our OAuth-based system, we've been able to manage those authentication flows with a manner that has passed review by a wide variety of security officers. Something that we perhaps didn't aim for in the beginning, but ended up being central, is this notion of supporting event-based processing. So having an event trigger the dispatch of a FuncX resource and the completion of a FuncX computation triggering other activities. And this ends up being vital in, as I mentioned, these experimental data analysis flows. The portability, I guess we've covered. We're starting to see sites, especially supercomputer provider sites, that tend to have very complex batch scheduled resource allocation schemes, also deploying FuncX as a way of using otherwise idle resources. So it's a way of increasing the efficiency of use of resources. And then the automatic scaling ensures that resources don't sit there unused when people are not making use of them. And then we're sort of pushing in this last direction. I'll say a bit more about that perhaps if there's time, but we want to be able to share function definitions with collaborators and share endpoints with collaborators, but not necessarily make them universally available. And those are things that our authentication and authorization model supports. So a few other things that, what have we learned? Also that are not negative, but lessons learned. I guess I should go in order. Of course, this function as a service is not suitable for all applications. And, when is it not suitable? Well, as with any function as a service, perhaps, especially one in which the compute is perhaps some distance away from your data, you have to be sensitive to the ratio of data size to computation. We're working on reducing that. Containerization is not the answer to all portability problems, and we're learning lessons there and hopefully working out how to overcome them. The allocation models that we use, in which we tend to start substantial numbers of workers to support a computation, works well in most cases, but very fine-grained functions, the scale-up time may be too slow to support some use cases. And then finally, of course, maybe it's obvious, but not every application is amenable to this decomposition into many independent pieces. This model was certainly useful for more than just embarrassingly or happily parallel, completely independent tasks. It can be used for pipelines, for example, but it can't be used for all applications. So to review a few other things that we've seen here. So, our goal, I guess, is to make it as we say here, to make it as easy to compute remotely as locally. And that's something, we've done with data, with the Globus services. It's easy to access data remotely as locally, or rather it doesn't matter where data is located in order to be able to access it. Computations, things are more difficult in some ways because of the increasing heterogeneity of computation, for example. And these, for example, complex authentication schemes. But we seem to be doing a good job of running things remotely. I think the things I mentioned on the previous slides are perhaps obstacles still to be overcome. Data management is worthy of further discussion. So our current FuncX system uses what is really also almost naively simple approach to data management, at least in most cases. A function starts on a computer. It is dispatched to a remote computer with its arguments. Those arguments are copied to the remote computer, computation occurs, and the results are then copied back via cloud staging to the originating requesting computer. And of course, you can see that that's wonderfully simple, but also is going to fail or not perform well in many settings. If your data are very large, if you want one function to execute on the output of I guess I should say a second function to execute on the output of a first function. Perhaps if your data is not in a form that's easily serialized, if you want your functions to be stateful. And a common use, for example, for that is when you have a remote function that is steering machine learning processes where, for example, you're involved in active learning. You're trying to use the results from a first set of computations or experiments to help decide what to do for the next computation or experiment. And so we're looking at integrating methods into FuncX that will support some of these things. For example, by viewing our data space as being not just the storage on my originating computer, but a large distributed data space that may span many different storage systems with the abilities for moving data, or at least suggesting where data should move within that data space. So one can use caching schemes, one can use high-speed data movement, and we're using Globus for that. One can use what we call proxies for objects. So we transmit proxies from one place to another and then only resolve the proxy when computational is about to be performed. One other topic of concern, and this, I should say, both the previous ones and this one are certainly object of much research at the moment by people outside our group and as well as inside our group. How to manage compute environments in very low overhead ways. So there's some nice container technologies, which I'm sure you know about, that are some of them quite widely used. These containers tend to be fairly heavyweight entities. And then there are the ones that are lightweight tend to be less secure. So we're looking at understanding those trade-offs so that we can effectively and securely sandbox executions, but also avoid the overhead of fully general containers. And there's a nice paper at IPDPS by Tim Schafter on what he calls lightweight function monitors that addresses some of those issues. And then another sort of you might also say mundane, but very important, frequently studied, but I think still work to be done issue is managing trade-offs between start time and resource utilization by managing using various forms of cold start, warm start, etc. In terms of acquiring nodes, instantiating containers on nodes, loading packages into containers, and then reusing those various elements. Reusing an endpoint, a set of nodes that have been acquired on an endpoint, the containers that have been instantiated on those nodes, and the packages that have been loaded into those containers. Lots of interesting resource management problems that computer scientists always seem to find resource management problems interesting. And so we've got students eager to work on those things. And then the last, something that we're just starting to look at is how to schedule function executions in a federated environment. So we have this, at Argonne, for example, scores of FuncX endpoints on systems ranging from little microprocessors to supercomputers, and we have an increasingly rich set of workloads. How do we map those efficiently onto those very diverse resources, diverse in their location, size, and capabilities? And I show a few results on the right that I won't go into in detail, but they show some experiments. A master's student did, mapping, doing round robin mapping of a workload, mapping to the fastest endpoint, or mapping to the endpoint that is predicted to have the smallest ETA based on a combination of transfer cost models and execution performance models. And of course, as you'd expect, each give different results. One other issue I'll just mention that we're spending some time on is working with a fairly diverse group of resource providers to understand how to address the security challenges associated with this federated function as a service. At the moment, individual users deploy their own endpoints on computers, but of course, as with Globus data endpoints, which are shared resources, that support powerful authorization models, so you can make data accessible to a single person, to groups of people, to anyone. We want to allow the same sort of models for compute endpoints, but that is going to require a mix of active controls and policy innovations. I mean, accessing someone's data is a nice thing to do, but being able to deploy functions onto a supercomputer is probably a much more attractive opportunity for an attacker. So one thing that we're looking at, for example, is approval processes for functions that are deployed onto some of these high-value compute systems. Other directions we're focusing on monitoring, logging, auditing. We'd love to talk to people about those things. Generalizing our authentication and authorization frameworks, and looking at how to manage these security issues, as I just indicated, so that I can create a container, deploy a function, and have some way of verifying that it is something that is suitable to run in a particular location. So, as I mentioned earlier, this is where you go to get more information to try running FunkX. And if you have any questions, this is my email address. So thank you very much for your attention, and hopefully there's some questions.
Thank you, Ian. Exceptional talk. I really, really enjoyed it. We already have a couple of questions in the chat. Others, you can follow the model. I'm going to read these two questions in the chat. You can also read them. I have some questions, and others can also ask verbally or type it.
I can read them, actually, yes.
Okay, why don't you do that?
Yeah. So first of all, from Kevin, thank you.
Would you mind reading it?
No, of course, I'll read it. So the first one from Kevin Azogba is, given that FunkX can execute a function on many different computing platforms of different scales, what resource allocation policy is used to ensure fairness, and how much processing power is allocated given the user's request for resources? That's of course a key question, and one to which I don't think we have an answer, but we're going to be ready to. Well, we are ready to implement various answers as supported by different resource providers. So, to give you some points that we might steer towards, of course, in the cloud context, resources are assumed to be infinite, up to a small value of infinite, perhaps for any individual user. And you use the fact that you have the sort of the law of large numbers to assume that those resources requested are always available, constrained by people's ability to pay. In a supercomputing environment, resources are allocated to people, and then they can request access to them by submitting a request to a queue-based scheduler. And the resources we work with here are probably going to be using a mix of those models. Some resources will be available on a first-come, first-served model. Others will be perhaps allocated to users based on some more formal allocation process, perhaps with a priority availability that ensures that at least some amount are always available. And this is as much what's primarily, I'd say, an economics and policy question rather than a technical question. But our goal is to be able to allow resource providers to express those policies effectively, and then monitor their effectiveness. A second question from Karul Kazmiran is, what happens if a compute resource, for example, my laptop, goes down in the middle of a computation? Is there a retry mechanism? Yes, there is. So, FunkX, functions are, modulo what I said about wanting to support stateful functions are stateless. They take some input and then generate some output. So the FunkX service can detect that a function execution has failed and then resubmit things. And we can specify retry mechanisms. And I don't recall what retry mechanisms we provide by default. If it retries automatically, has a exponential back off or something like that. But retry mechanisms are certainly available.
Ian, to respect the order of questions, Paolo Farboski raised the hand, and we can go back to the chat after that.
Oh, yes. Please.
Hi, Ian. Great talk, by the way. Yeah, so I was, following up basically on the previous question, I'd like to understand a little bit better what are sort of resilience mechanisms. And I understand this is a different paradigm, but, if you're running HPC jobs, you may want to, suspend them all and preempt them and restart them later if some higher priority job comes in. Or, as you said, kind of what's the moral equivalent of a checkpoint restart here? Is there such a thing, or we got to start thinking about a completely different paradigm?
Yeah, that's a really interesting question. So if you think of, what FuncX knows about basically is the pool of requests that have been submitted to it, and for each of those requests, what its status is. Is it running? Is it queued, running, or completed? And so, it would not be difficult to, or checkpointing individual function executions is not something we've considered. I guess if the container supported it, we could do it, but certainly it would be easy to say to FuncX, just stop running this bag of this collection of tasks. Kill all the ones that are running and add them back to the bag, and then restart it at a later time. So in that sense, it's quite similar to checkpointing a regular computation.
But you can guarantee that no message has been sent in the middle, since is kind of all data flow execution that it's completely stateless to the end, because otherwise you got to have to buffer intermediate messages and undo messages that have been sent halfway, so that if you restart, something like that, right? I mean, it depends if.
Yeah, so I think speaks to something I mentioned earlier, our interest in moving beyond or supporting something in addition to this purely functional model where data sits on my laptop and is dispatched to a function, and then the result returns back. If we allow for intermediate products to sit at intermediate locations, things get more complicated. So we're still trying to understand what applications might motivate that, and what are the trade-offs between purely completely persistent state and perhaps intermediate states. We might want to allow people to express, for example, that certain collections of tasks are groups, and they need to be, if they fail, then they need to restart from the beginning. And while others are perhaps guaranteed to move their data to persistent storage.
Thanks.
Okay, we have another question in the chat, Ian. You want to?
Yeah, so Marco Neto asks, could you please talk a bit more on the challenges of adopting function as a service for users who have traditional HPC applications, e.g. written with OpenMP and MPI? Well, my first response to that would be, we're not aiming to replace the use of OpenMP or MPI at all. Instead, we're typically aiming to support new sorts of applications. So, for example, one that sort of speaks to the OpenMP MPI use case is some colleagues who are developing a system for machine learning based design of materials, and so their state is a collection of machine learning models of materials properties. They use those models to decide what material to predict next, and then they dispatch to a computing system an OpenMP or an MPI computational chemistry application. So we have this function as a service sort of workflow that is invoking potentially large MPI or OpenMP computations. I mean, certainly, so the question of whether there are general techniques we might use to take an MPI application and decompose it into components, it's not something that we've considered, and I'm not sure that it would make sense in general, although I'm sure we can find cases where people have happened to have used MPI, the message passing interface, to implement what is basically a very loosely coupled computational structure.
Did you look at energy consumption?
Oh, that's a great question, and the answer is no, not really. Right, so so that you could look at that from many aspects, but one would be you could dispatch functions to low energy consuming computers. So that would be a good thing. Moving data to remote computers could consume more energy, and that would be a bad thing. So it will be interesting to consider both those aspects.
Okay, we have Ian. We have Alfredo Goldman asking question, and then I have a few if there's time.
Yeah, thank you. Please go ahead.
Okay, thanks for the great talk. My question was about energy also, but not only energy, but costs. For instance, if I do not want something so fast, maybe I can wait a little bit more and pay less. So I imagine that the answer is the same that you already gave.
Yeah, I think so. So far we're focused on making. So far we've been focused on making the movement of tasks and their execution, completely simple and reliable, but not leaving it to the user to decide where to send things. But we believe, as shown by that one slide, based on our master's student, that it then becomes feasible to, explore some of these alternatives.
Okay, so I have 3 questions, but they're going to be pretty quick. Based on your experience, and you did say that not all applications are well suited for serverless or function as a service. Do you have any recommendations? What is the granularity that is still worthwhile doing it, or any guidance to the programmers?
Yeah. So, and of course, that's the answer to that question will depend on the characteristics of your function as a service system. FuncX is every request currently goes via the cloud, and there's some management overhead. So we tend to recommend that functions run for at least tens of seconds, not just seconds. There's no reason why we couldn't greatly reduce those overheads by various forms of caching and edge execution, but that's not something that we've prioritized at the moment based on the workloads we see. If you're using a commercial centralized cloud provider function as a service, I think the overheads are significantly less at the moment, so that would suggest somewhat smaller sizes, perhaps a few seconds.
And the last 2 questions are really very related, and they go towards longer term executions. Did you track the lifetime of your services or endpoints that are available, or are they long-term running? And do you recommend forming, for example, dynamically or runtime binding workflows out of existing services? And if you do so, do you also intend or already do support versioning?
So first question, right. I'd say we haven't looked too much at lifetime. Of course, it's a very important question, but again, very policy driven. You'd expect to see probably a pretty broad spectrum of lifetimes, depending on the policies of the individual resource providers, and probably along a couple of dimensions. One is how well are the resources run, and secondly, to what extent are these resources provided, as opportunistic resources, for example, on supercomputer centers that are, or any resource provider that's trying to use function as a service just to soak up unused resources, versus a provider that views that as a first-class citizen. So that's, I think it'll be interesting to see how that evolves over time, and we will be monitoring, the lifetime, and we will be gathering data as time goes on. And then the second question is about versioning. So versioning of functions is something that we are addressing. We've got a somewhat separate project that is developing these techniques particularly for experimental science, and I referred to some of the results here. And there we have very strong versioning methods, where every time you publish a function, you get a new UUID, because we did find that we were seeing some collisions of among popular functions.
Well, thank you very much, Ian. It appears that we exhausted the list of questions and we ran out of time. Extremely interesting talk, and thank you very much again. If you don't mind sending me the slides to put them on the website, some people already requested. Otherwise, for everyone's information, we'll put the recording. Again, thank you very much. Highly appreciate you staying this long.
Okay, thank you. Bye-bye.
Thanks, Ian.
Thanks.
Bye, everyone.